All right, we're going to start. Okay. Welcome, everyone. Natasha is out today, so I told her that I would help moderate the session. This is Hamed Muftakari from. He just recently started at UA in August. He did his PhD at Portland State in civil engineering and a postdoc at UC Irvine in the civil engineering department. And he's going to speak today on a topic that if his presentation was open, I could tell you what it was. But he's going to talk about multi-hazard coastal flooding. Go ahead, Hamed, take it away.
Hello, everyone. Good to be among you this beautiful Friday. So, is this something that I can move from, or I need to use the keyboard?
Oh, you?
That's fine. That's fine. Yeah. So, the title of presentation today is Multi-Hazard Risk Analysis in Coastal Regions, and I'll start with the definition of risk. Because when we go through the literature, we will find different definitions for this term. But one common approach in engineering is to say risk is the product of hazard, exposure, and vulnerability. Hazard is the probability or intensity of a damage-producing event. Exposure refers to the population or value of assets exposed to the hazardous situation, and vulnerability simply refers to the harm or loss. But in coastal systems, we have a tough job to do, as the system is so complex. There are many drivers, rain-driven, and coastal processes that all together interact and interplay to produce hazardous situations. Also, in these systems, in a changing community, changing world, and climate, population, whatever, we are dealing with hazards that they're changing the statistics over time. So we need to deal with two important aspects of hazards. One, compounding effects, the other, trending nature of hazards. The time varies. And if you look at this index that pop-up slide, you'll see in every slide which specific aspect of risk I'm talking about. So right now I'm talking about hazard, and more specifically, compounding effect of hazard. But what I mean by compounding? Intergovernmental Panel on Climate Change says, if two or more simultaneous or successive extreme events, or combinations of extreme events with underlying conditions that amplify the impact, or a combination of events that are not themselves extreme but lead to an extreme event or impact when combined. So, these are mainly referred to compounding effects. One example is, in this case, storm surge at the coast and the local rainfall intensity. When you look at the statistics, you will see a significant correlation structure between them. And the reason, one explanation is that they both are driven by the same climate processes. What it causes, what is the impact? The impact is, we've designed this storm drainage system to drain a designed rainfall to the ocean outlet during rainfall event. But when during the compound event, we experience both coastal high water and rainfall in the watershed, the system fails to drain rainfall and leaves the community flooded. That's what we mean by compounding effects. When we look at the costliest U.S. climate disasters over the past couple of decades, the largest are Hurricane Harvey, Katrina, and Sandy. Both Hurricane Harvey and Katrina are classic examples of compound events. Why? Because a low atmospheric pressure event both gives rise to the coastal ocean water level, at the same time dumps huge rainfall on the coastal watershed. So they both interact to produce very costly and hazardous situations. Some recent examples: Florence, September 2018. This is precipitation. And this is the river flow observed near Kelly, North Carolina, up there, upstream Wilmington. And you see the water level in that gauge goes beyond some historic thresholds. At the same time, at the coast, we experience around 4 feet of storm surge from both sides. Another recent example, Hurricane Michael. We are hearing about it these days. So, in October 2018, in Apalachicola River, I still have a hard time reading that name. So, this is the precipitation, and this is the discharge just upstream of this area. And you see the discharge goes up to something near 50,000. This figure is new for this morning. And this is the surge. 8.3 feet of surge right here. These together, that's what we see through these tapes and movies and Facebook and news outlets, how this flooding occurs. So, all these motivated us to look at the flood risk assessment in the United States. One, there are limitations with univariate methods because univariate methods mainly focus on one variable at a time. So if you're gonna analyze the return period of Sandy, Katrina, all these hurricanes, using univariate methods, you need to analyze the return period of precipitation, rain runoff, or coastal surge. Using univariate methods, you cannot look at both parameters at the same time. Also, if you look at the current flood hazard assessment practices in the US, they are mainly developed based on univariate methods, not multivariate. And it probably partially explains why FEMA failed to capture 75% of flood damages in Texas over a study period. And so there are also other evidences that we need to look through the way that we basically characterize flood risk. So in a study, we analyzed the data for 8 coastal watersheds along the coast of the United States to see how this interaction would affect the risk. And basically this is first half of my presentation today, talking about compounding effects of sea level rise and fluvial flooding. Is already published, so you can see the more details in that paper too. But I will take one step back and to see what I mean by univariate versus multivariate. In univariate metrics, we usually have a time series. This time series, we calculate probability density functions and integrate to calculate cumulative distribution functions. And using these CDF curve for any given design return period or so, 1 over return period is equal to the exceedance probability, which is 1 minus CDF, and we calculate the discharge for designing levee, storm system, whatever we have. This is sort of common based on univariate methods. But in bivariate frequency analysis, we not only need the frequency distribution for each of these parameters, which in this case we call the marginal distribution, but also we need to know about the correlation structure between these variables. And the way what we do it, sort of similar to univariate, but in higher dimensions. So this probability density isolines basically explain the likelihood of co-occurrence of these variable x and y. X could be fluvial flooding, y could be coastal flooding. And when we integrate over these curves, we end up with these curves, which are called cumulative probability isolines. Each of these curves are associated with a given design return period. Exactly that's what we do here. But the difference is that in here we have one design value. Here we have infinite combination of x and y along each curve with the same return period. So we need to make sure that we cover a range of occurrences, not only one event. One novel approach that we use in that paper is that when we look at this charge versus water level, and that in case of hurricanes, if we employ univariate metrics, we end up with a threshold below that is considered to be safe, above hazardous. For water level, the same threshold using univariate metrics. But in multivariate or bivariate techniques, we end up with this curve that explains the situation that both discharge and water level goes beyond a certain threshold. We end up with this area, right? When we look at the case of flooding, however, in case of extreme flooding, we need both these variables go beyond a certain threshold, but not always. Because if either discharge goes beyond a certain threshold, or water level goes beyond a certain threshold, or both, in all these three situations, we end up in hazardous situation. That's the idea behind developing these curves called bivariate or hazard isolines. Basically, it calculates the probability of having the pairs within these three shaded areas versus this classic area. And so let's look at the results and see how these make difference. In this case, this is an example that this is a threshold, the return period of 20 years for discharge, return period of 20 years for water level. Look at the combination. If we consider, basically disregard the correlation structure between variables and consider them independent, we end up with this black curve. And for the same event, we end up with a return period of 10 years. But if we, using calculus, which I'm not going to go into that direction today, basically appropriately characterize the correlation structures and quantify the return period, joint return period, we end up with this red curve, which estimates 16 years. You see, taking three different approaches, we end up with three different numbers. That's why these are still here. What was the return period of Sandy? Because it depends what metrics you use and what approach you take, what assumptions you make to end up with these numbers. And in terms of failure probability, which is more interesting to engineers, in univariate approach, we have this equation that shows the return period for a given design lifetime of P, and the event with the extended probability of P would be the equation at the top. But in multivariate situation, it's not that easy because we're dealing with number of parameters along with their interactions and correlation structures. So what we do is, if S1 is the hazard scenario associated with driver number 1, S1C is its complement. So X1 is a member of S1C, means we are safe from driver number 1. Then if we make sure that we are safe from driver number 1, 2, 3, 4, this probability is the probability of being safe. And 1 minus probability of being safe is the failure probability. And how we calculate this probability? Using those couple of functions that I explained earlier. Just mentioned earlier. And let's look at the results. In this case, if we employ univariate approach, we end up with this black curve. With multivariate approach, we end up with failure probability almost 10% higher. But another issue that I'm going to highlight here is trending nature of hazard. If we bring the impact of sea level rise into effect, you see, by 2050, for this given system, what would be the failure probability? Significantly different. So this is something we need to consider when we employ statistical analysis, because in most cases we assume that the statistical parameters are not changing over time, which we're dealing with time variant hazards, and we should be careful about making these assumptions. And this work right now is part of ASC manual on adaptation to climate, changing climate is recommended in that.
Where is the sea level rise included in the multivariate equation that you have above? Is it in there, or?
Basically, what we did here, using these couple of functions, we characterized the correlation structure. Then, in that paper I've explained in the methodology section, we basically perturbed the water level with higher sea level scenarios. Because we have those values of water level based on current mean sea level, and we can statistically, using Monte Carlo simulations, we can perturb those water levels for higher values, and then However, with the assumption of making the assumption that this correlation structure remains the same if in known future, because it makes it much more complicated. But technically saying, by perturbing y value and calculating those probabilities. So far I talked about compounding effects only. Now I will talk about trending hazards more. One example that I like to bring up here is nuisance flooding. This is a figure from a recent paper, definition of nuisance flooding. Nuisance flooding by definition is a few inches of water on the ground, doesn't cause structural failure, death, or injuries, but public, basically socioeconomic impacts with business interruptions, traffic interruptions. It's annoying. It's nuisance. So, why I brought this example? Because in the past we had this syllable, and we needed tide on top of that wave surge, whatever, to cause nuisance flooding. These days we have this much of sea level, and in the future, maybe higher. That's why you hear about tidal flooding, or sunny day flooding, or clear sky flooding. These are all different terminologies referring to nuisance flooding. At the time of high tide, there are communities on the East Coast and the Gulf Coast that experience up to a couple of 100 hours of nuisance flooding in a given year, and it's expected to be higher. This is an example of trending hazard, and they have significant infrastructure impacts, roads, stormwater, sewer systems, whatever. They're impacted by these kind of events. In the following slides, I will bring some strategies that we can take to tackle these non-stationarities and trending hazards. One of them, extending our knowledge. The more we know about the past, the better we can predict the future and plan for the future. This is an example of my PhD thesis, and we looked at the interaction of freshwater inflow, red curve here, and tides within an estuary. We know at the coast these two interact, and the way they interact, when water discharge increases, river flow increases, tides are dampened. They shrink, they lose energy. So you see the amplitude shrinks when discharge is going down. See? This is the basic concept behind this work. And we use these information to extend our knowledge about the hydrology of San Francisco Bay back to 1850, because the freshwater inflow to the San Francisco Bay is available 1930 forward, but the tides for navigation purposes, whatever, is available at Golden Gate back to 1850. We use that information to extend our knowledge about the hydrology of that system for another fold. So it's really working in that system, and using that, we could basically compare the historic hydrographs, annual hydrographs, versus current hydrographs, and show that not only the seasonality is changing, but also the volume of water ending up into San Francisco Bay is 30% lower, and also about sediment load, we did some time tests. But the idea here is that extending knowledge is useful. Another strategy, numerical modeling. When we expect that Mobile Bay is going to be dredged, its sea level is going to rise, what we can do, we build a numerical model to see how the system is changing over time with response to these changes. The population, the landscape, whatever. Another useful strategy, non-stationary frequency analysis. There are a bunch of tools out there that we can use for non-stationary frequency analysis. What is common in these approaches is that they weigh the pre-assumption of stationarity in distribution parameters. For normal distribution, for example, we have two parameters. For GV, we have three parameters. We assume these are stationary over time, while if we weigh those stationarity assumption, we end up with some sort of these results. In this case, I analyzed the water level at Boston, and it showed that a 3 meter of water level has a return period of 50 years in mid-1930 or so. Right now, the same water level has a return period around 25 years, so it's becoming twice more frequent. This is an example of applying non-stationary frequency analysis in practice. Another useful approach, molecular simulations. We have, for example, this is the case of nuisance flooding. So we have sea level anomaly, which is the change in mean sea level over time. And these are the frequency of nuisance floods in New York and Washington, D.C. And we have some projections for sea level rise. We can sample these distributions using molecular simulations. And based on the tools and relationships that we governed earlier, to see how the nuisance flooding will respond to this change. And in a case like Washington, D.C., which had up to 200 hours of nuisance flooding in a given year so far, it's expected to increase up to 700 hours of nuisance flooding. And so these are just some projections that we can make using molecular simulations. Okay, now let's go beyond hazard, because as I said, risk includes more components. Exposure is another component. And so let's see how we can have a better understanding of risk, including both these components. Hazard and exposure together. In case of nuisance flooding, business interruption, traffic interruption, so on and so forth. Let's look at the impacts. If you look at the impacts, the cost or exposure associated with infrequent, rare, extreme events is much, much, much higher than these frequent incidents like nuisance. But in that paper, we've explained and brought up an index called Cumulative Hazard Index. Using this index, we integrate under the curve for two different categories of events, and we compare them. And to see if the accumulation of the costs of these highly frequent events compared to those infrequent events are equal or even greater. Because this is like throwing a penny while you're walking. You might not care for 1 day or 2 days, but when it leaves your community flooded a couple of times a week, so you should be concerned about it. And we compared this index for different, we calculated this index for a number of systems. And on the East Coast, for example, New York, Washington, and Miami, Florida, they come up with positive index. Means accumulation of costs associated with these over time are somehow comparable than those extreme events we are usually about them, but we don't care about them. So this is something that we propose in that paper, but and also an example of cumulative hazards, what we mean by cumulative hazards. Another example, infrastructure exposure. We usually have sea level rise projections, and we have climate projections that derive wind fields and calculate the surge a couple of years from now. Each of these have their own distributions and uncertainties. In this work, we propose to see, okay, when I'm going to talk to a stakeholder, to owner, to city manager, whatever, ask me, what is the likelihood, or whatever, what is the risk of flooding in this case? I cannot say, these are the distributions of drivers, and I need to put them all together. You decide what to do. It's not what they want to hear from you. What we propose here, we looked at we simulate, basically hindcast the water level. This is the case in Los Angeles. And the brown curve is the observed cumulative distribution function of water level. And this is the flooding threshold, this blue curve. And this green one is our historic simulation based on climate projections that we have. From all these climate projections, we have historic simulation and also future projections. So if we employ the Bayesian model averaging techniques, finding the weights out of these simulations, and we end up with this curve, which is fairly compatible with the historic. So basically this validates our model that we can use for future predictions. And this black and red curve, these are future projections under RCP, representative concentration pathways, 4.5, 8.5. And these are basically the percentile of sea level rise that we take for future predictions. And if you see in this case, for example, when exceedance probability was around 5%, used to be in that system historically, given surge activities and sea level rise activities, it could increase up to 20%, which means 1/5% compared to 1/20%. You see the difference. And so, in terms of impact, we quantified what does it mean to a city manager in Orange County. They're going to plan for road infrastructure, transportation infrastructure, water infrastructure. This is simulated historic. It shows up to 35,000 km/h of flooding, any category of flooding, in the past, which under future projections of surge and sea level rise, it could be 2 to 4 times higher. This is the way that we basically can translate those distributions and projections into something digestible and communicable to stakeholders. And I talked about compounding hazards, changing distributions, trends, whatever. One thing we usually do not consider is cascading effects. Cascading means when something happens, like in California, we hear that, not only in California, so many other places, that wildfire happens during dry season. And in the wet season, that will be precipitation. When we're going to design that system for flooding, we look at the frequency analysis results of precipitation and design that system. But there is a significant difference if this system has had the experience of wildfire or not. That's what you see in mudslide in California and everywhere else. This is one example of cascading effects. In case of tsunamis, earthquake followed by wave. There are many other examples. In this paper, we basically brought up some examples of cascading effects, which are not taken systematically in risk assessment. And it says, chains of adverse events cascading like toppling dominoes will become more common as the world warms. Yet the scales of cascading risk are still unknown. Risk analysis estimates like the likelihood of single events, predicting rising frequencies of droughts, hurricanes, and so on. They do not consider the web of connections between them. This is basically a call for better understanding of the risk. Prior experience needs to be part of the story. And at one level, the vulnerability at one level is basically a hazard at another level. So when we say the area is burned, this is vulnerability for forest. But for hydrology, this is a hazard driver because it leaves soil exposed to flooding, and so on and so forth. So this is something I was just going to highlight at the end of the talk, and thank you very much.
All right, questions?
So you had shown really nicely how you really need multivariate statistics to address these complex systems. Have you also considered using fuzzy logic? Would you see that as potentially beneficial?
Honestly, that's not something that I have personally experienced. So I think there is potential to the extent that I have knowledge about fuzzy logic approach, but that's not something that I can provide detailed answer how and which way of fuzzy logic. But I know there are many experts in this room that they can provide much more details, but I personally have not done that.
I have another question, just about, so you had shown, you make these assumptions about the systems and how these variables relate to one another as you're doing these projections? Are there any thresholds at which variables would, those relationships, those parameters would completely change? Especially in relation to sea level rise. For example, so this is an example that the Mobile Bay basin experienced about 8,500 years ago when the bay formed. It's a shallow valley, right? It's an old river valley that when sea level was rising during the 8.2 kiloyear event, it crossed the threshold and it flooded Mobile Bay and formed this shallow bay. So that I see as a geologist as being a threshold for variables completely changing in these systems. Do you have any of that kind of logic or understanding built into these models?
That's a very good question. Actually, that's what I've seen in the literature. They call it also tipping points. That if the system reaches to the level, the dynamics could drastically change after and before that. So the work that I proposed here today was mostly based on the assumption that we have not met such tipping points in our system. And as you mentioned, in geological science and other sectors of science, usually people can go backward in that. But one thing that I'm just sharing my perspective, it's not something definite. What I understand is that right now we are dealing with very complex systems which are not only under natural forces. Human being is a significant component, and human nature interactions. We have parasitic events, talking about climate, temperature. I think my understanding is that one motive behind these movements and international collaboration is let's not to get close to those thresholds and tipping points because we don't know what's going to happen after that. Let's stay in the area that we know the most. However, there are scientists who are working on different ways of representing future. If something happens, if there is this level of sea level rise, if we reach this level of there are some tipping points. What would happen? I think there is so much uncertainty on the other side of that tipping points. Even if we can quantify them correctly and accurately. But I think those research topics that I highlighted today are mostly with the hope that we do not reach those tipping points.
Yeah.
What's going to happen after that? There are so many unknowns.
This is why we have to look at the past to understand what those are.
Exactly.
To better predict them.
Exactly.
So you've characterized risk in California with mudslides and fires, and in Oregon and Alabama now the hurricanes. So in your opinion, where is the, I guess, safest place to live in the U.S.? We're all gonna do it.
Honestly, to me, when I'm thinking so far, I kind of lived in Oregon and then California. I think this can be so.
There is a map over where someone has calculated joint probability of that. Least earthquake and all that.
Yeah, at least for my research purposes, I couldn't find a multi-hazard situation. If there is tornado, it comes away and goes away. Yeah, you're dealing with one variable at a time here. But I don't know, nobody, let's say nobody can answer, but I love Oregon, I love California.
So
I
you are
love
giving
Alabama.
fuzzy answers. That's what you're asking.
So you want to add something?
Well, I just want to say fuzzy logic is more on the possibility side of things. What Hamid is mentioning is on the probability side of things. These are two different things. There's a difference between possibility and probability. And on probabilistic approaches that Hamid was presenting, we work on frequentist approach or Bayesian approach. But in fuzzy logic, we work on the relative truth.
Right.
So that's completely different. I don't think that fuzzy logic fits well here,
Okay.
just from experience.
sort of follow up on what Becky asked, I mean, could you use this type of analysis to actually identify a tipping point? Say you're looking at historical data and projecting into the future. And would you actually be able to identify a tipping point, or does the analysis assume that everything is constant?
We do not make the assumption of constant characteristics, but taking non-stationarity into effect doesn't mean we have taken those tipping points into account. Again, I think those tipping points are more toward the basic science than applied science, and you need to bring the physical dynamics, modeling issues into there are definitely some probabilistic approach into that to inform what is the likelihood of these situations to happen, then these follow up. And there are something that we have observed. For example, I'm during my postdoc I was supervising a PhD student. He was doing some CO2 emission analysis based on field observation. And so, okay, up to 18-20 degrees is based on the moisture, soil moisture and temperature, will have some increase in CO2 emission. After that, there is a tipping point. And after that, the activities and those parameters that that are responsible for CO2 emission, they will downgrade. So there is a tipping point. There are some tipping points, but if you look at the classic literature of CO2, they are always exponentially increasing. In that work, we should know. Seems like there is some tipping point. However, it might be regionally different, depending on the characteristics of the system. But we should also consider those tipping points into account. So, here and there, we might see some tipping points through the statistical analysis too. But talking about some story-changing tipping points that change the whole world dynamics or whatever, I think that is a sort of definitely transdisciplinary analysis that needs to take into account dynamics at different scales and how these systems are working. I think it is so sophisticated to find these tipping points.
So what are the ramifications on engineering design? Let's say I want to design a culvert or a grade inlet or a stormwater system, right? And I'm a city manager, right? I'm using the basic intensity duration curve or basic single event based, right? Now, you're telling me it's going to compound, and it's not just sea level. You could have a antecedent condition, moisture condition. There are so many other things which can compound, right? With all this, now what is the design flood I should use? I mean, now I'm completely confused. At least we were all agreed on some manual which has got some number I can design, right? So how do we take it to practice, basically?
So I take this question an opportunity to invite you to take this class. This is open channel. I'll be teaching this spring, and it's about hydraulic design of culverts, whatever. So I just used the opportunity.
Sure,
to
yeah.
advertise this
Good
course.
timing.
Yeah, thanks for asking. And so I think there's a long way going from scientific design approach, whatever, into practice. But I'm optimistic, at least from the feedback that we've heard so far. Again, the approach that we proposed in PNAS in less than a year has been part of ASC manual right now. And in that Nature article, we highlighted the gaps, and we hope that these gaps to be seen by those who are responsible. So I mean, as scientists, we need to provide robust approach. But we are dealing with human beings who are in their office, not necessarily open to any new ideas. But I think there are some, at least the way my understanding is from research perspective, NSF, NOAA, Army, USGS, they are trying to basically bring these research ideas into practice. They have manuals, they enforce policymakers. This is a complicated situation. It's not something that I can say, okay, you go take this. But I think from a scientific perspective, as an academician, I think we better be able to, besides basic science, from engineer perspective, also communicate the science well, to let them know and make ourselves familiar with what they're doing. You know, we should not also, from our side, we should not sit in our office too and do research. We should go to the field. We should talk with them. We should know about their concerns. And I think those agencies who are responsible for funding, to me, they're doing a relatively good job in bringing those questions into practice and bringing up who can answer these questions. That's my understanding. I'm not saying this is perfect. Yes, we're working in a world with human beings at their own characteristics and situations. But moving forward is something that we should always
So to summarize, would you say that, I mean, if I'm designing a culvert, I mean, obviously every engineering design is designed to fail, right? That's the whole idea. I mean, it's going to fail at some flood event.
Mhm.
It's not, otherwise I gotta put this huge culvert, which is so expensive, I can't afford it, right? So there is a compromise, right? So I'm just wondering, like, how does all this knowledge going to kind of, I mean, maybe you can even speculate. I mean, I can intuitively say, well, we probably have to design for a much bigger flows, right? Or which means the bigger culvert and all that thing, right? But somehow rationally, how is it all going to kind of gel into some sort of a design manual or design standards?
So I love your questions because you helping me bring my slides on reserve.
Okay, there you go.
So this is a paper we
It's all
have
plot,
under
right?
review.
We talked about it, okay.
And if you look at these, you know what we did here, it's on the review still, but we are trying to figure out how we can help those designers to look at the compounding effects. This is a MATLAB toolbox, user-friendly, and this is a chart that we've provided. And parallel with this, I'm working with officials, those who are responsible for flood modeling in Marin County, California, and I was working through AGU sort of voluntarily. And what I was trying to figure out, that was the motive behind this work. We are doing sophisticated frequency analysis, but for those in practice, they don't necessarily need to know every single detail. Through such simple chart, we are trying to provide step-by-step. Okay, how to sample the data, how to see whether if there is significant correlation or not. If not, the current approach that you're taking with FEMA should be fine. Don't be worried about, and Marin County was the case that we end up with this conclusion. They're fine. They don't need to go through sophisticated approach. In case you need to go through that, there is a MATLAB toolbox. We will be happy to share. We have listed a few literature around that to make them familiar with the basics, and then they can use the toolbox, then end up with design return period and stuff. And for example, in this work, basically this curve combines those joint PDFs that I showed you and joint CDFs together. So these curves not only is associated, this is not only associated with 50-year flood event, but also you can see the change in likelihood of compound events from 0 to 1. So using such simple curve, somebody can decide what would be the design events. And I've shown that, okay, as a designer, as a scientist, you can end up with this distribution for the design. But as a designer, if you run your system for these 3 events, you'll be safe. You're taking both tails and mid distribution. So there are ways. and this is an example that if we can provide, we can communicate what we do to practitioners, but I think we should be proactive to understand well how they perceive, and I think PE exam is a good way. Like, you know, when people are gaining experience and well, while they're in academia, they make themselves familiar with the basic concepts of design the engineers are dealing with, attending conferences, and so I think this is my answer.
To go back to tipping points for just a second, and just for a second. So I mean, you're doing extreme value analysis, right? So I mean, you could introduce physical covariance, right, in the parameters of your GEV, and then you could look at how changing those values of physical covariance affect your probability of failure. Right? So then you could see if there is changing whatever it is, CO2 or an ENSO index or whatever it is, how is changing that value suddenly maybe going to drastically affect my probability in that high variance space, perhaps.
I both agree, and I have some complementary information with that. To my understanding, there are some significant assumptions between those covariate GEVs also. They are all though based on the past. So for the future, relying on those statistics only, that was my comment, may not be sufficient. We should somehow go, accept the system has experienced some, as she said, extending knowledge. If the system has already experienced some of these tipping points, at least one of them, we might incorporate it into a statistics. But relying on the statistics of a system that has not experienced a tipping point would be something may not be sufficient to make any conclusion. That's my understanding.
Yeah. So early on, you showed the one of your first figures that showed the inundation of the stormwater outlets.
Yeah.
Yeah. So do you know how common that condition is, and how close, you know, in coastal areas? Is that really a pressing concern for many of these stormwater systems, that they're not able to drain when there's a high tide event, or you know, one of these major inundations? Is this figure from one of your papers, or is it from something else?
No, this is from city in Florida. This is on the map.
Oh, okay.
Yeah. So the city made this figure. I did not. So it has been
Yeah,
their concern.
because I'm just
already.
saying, I mean, that's a very relevant data point. You know, the elevations of all those outlets would be very relevant to this analysis, and very site-specific as well, right?
Yes.
So it might really affect the vulnerability of their, you know, of their system.
I've honestly have you know, when you go to like AGU conference, or there are multiple webinars that I myself have heard a couple of times about these issues in different cities across country. It's not just about here. There are a group in San Francisco, Berkeley group, they're working on that. The same here in Florida and North Carolina, I was visiting last year, they had the same. So probably I don't have a number proof for the whole nation, but I expect this
Yeah,
is and would be a serious.
And it sounds like cities, to some extent, are aware of this problem and conscious of the problem. Okay, that's great. So
That's why they.
yeah, they might even be able to provide the data if you were, you know, analyzing a particular situation.
Yes.
Just want to add maybe a question mark. So this is true not only in coastal systems but also in inland systems. I've heard in Chicago they talking about how changes in Lake Erie and all of that has an effect. So the water backs up in the stormwater infrastructure and causes pump out.
Yeah, I was.
It's very much relevant to inland stuff as well.
We had I have a friend who is in the University of Illinois Chicago. He was saying that we are in a flat area, so slope is pretty low, so that was one thing he also brought up about Chicago.
Okay, any more questions? All right, thanks, Hamed. So, I assume we're back next